61A, lecture number 23, Q&A.
So here we've got fall 2019 midterm 2 question 4, and I think we'll just go through it. Implement stable, which takes a list of numbers as a positive integer k and a non-negative number n. It returns whether all pairs of values in S with indices that differ by at most k have an absolute difference in value of at most n. Okay, so numbers near each other in the list need to be near each other in quantity. The functions that aggregate iterable arguments on the midterm 2 study guide have the following behavior when empty list is 0. Okay, great.
Is this saying, John, like it's sort of sorted?
Yeah, kind of sorted.
Kind of sorted,
Except
right?
it can go up and down a little bit, but
Yeah, you go,
like,
yeah,
you can
okay.
have two numbers that are very different next to each other, I guess.
Right, cute.
Okay, so let's see what we have. A bunch of numbers that are all near each other. All adjacent values differ by at most 2. There's the 2. There's the adjacent, and so we get true. And then we have an example that says same numbers, but a different k. This says even numbers that are 2 apart, like 3 and 6, or 5 and 2, are supposed to be only 2 away from each other in quantity, and that's not true, so we get false. And this last example has 1s and 5s next to each other, and that's bad. All right, so what are we going to do? Well, go through all the numbers is what this says. Well, actually, this goes through all the indices. So we get all the positions within S. We're going to get a range of other positions, and it's called near, which I think is an indication that these are the numbers that are kind of just before it. Why just before it? Well, it goes up to, but not including I. And then we have an if statement and some big gnarly expression that we need to fill in. And then we return false. So this general structure, which says for a bunch of examples, if we find something is true, then we return false. Otherwise, after we've gone through all the examples, if we never found something that proves it false, then we return true, is kind of a typical structure for checking some condition about every position in a list or something like that. So you go through all the positions in the list, you look and see if the condition is violated. If so, you're done. And if you never find such a problem, then you have decided, well, it's stable. So what is this condition we're going to look for? We're going to look for two numbers and where the difference is too big. So the way I would think about this is to say, let's pick an I. We're going to go through all the I's. So let's pick I equals 0, 1, 2, 3. And just as an example. So if I is 3, then we need to be able to detect that 5 and 2 are too different from each other. So what are we going to check for all the other values, j? We're going to have to check 1 and 2. Compare S1 to S3 and compare S2 to S3. So that helps me figure out what my range is. If this is 3, then I need to go from 1 to 3, which I think is I minus
What's the, is it K or N?
N is
K.
the magnitude, and K is how far you go. Now, we kind of don't want to go off the beginning. So it might be worth saying, I don't want this to ever be smaller than 0.
And John, can you explain why you're not going in the other direction? Like, why are you only looking backwards, not forward?
Oh, good question. Yeah, so this would only look backwards. And if you check each number and everything before it, since this is kind of a symmetrical check, that's the same as checking each number and everything after it. So you kind of don't have to do both. Even though the condition is described as pairs of elements, it's fine to get all the pairs of elements by taking each one and then the ones before it.
We could have also changed the range not to start at 0. We could have started at a K. There's no reason, because the first, then we wouldn't have to worry about that max, but I think it's fine the way it is too.
Yeah, I'm sure there's other ways to write that. Okay, so now we need to figure out how to check for this condition. Well, let's see what we have. We're building a list comprehension that says, is something greater than n for j in near. So j and I are both going to be bound in this expression right here. I was bound up here to 3. J is bound down here to 1. And we're trying to figure out whether that pair of indices causes a problem. And that problem would be if the absolute value of the difference between SI and SJ is greater than it. So this expression is going to give you true if there's a problem. And it's going to check each index in turn for all the different j's, 1 and 2 in this case. If any of those is a problem, then there's a problem with the whole sequence. So that's why we will aggregate with the any function, which takes in a list of true false values and tells you whether any of them is true. If any of these differences is bigger than n, then the whole sequence is not stable.
Then someone asked if I could explain the near part again.
Yeah, so near is supposed to, I is already set for us. And so it's going to go through from 0 to 1 to 2 to 3 to 4 for these examples. And for each of those ending values, we're going to consider other numbers that are nearby. And we need to come up with a range of indices for those other numbers. And we do that by computing how far back do we have to go from I. If we went back to 0, that would be too far. The condition is only about stuff that's nearby. And then I think it's worth just thinking about examples. So if I is 3, when I is 3, then what we really want is a range from 1 to 3. So we can get, I'm doing this example, this center one, so that we can get the 2 and the 3 and compare that to the 5. If I is 1, then we really just care about the 0th position. So that will be a range from 0 to 1. If I is 4, then we'd care about a range from, okay, so I is 4, we care about comparing that to the 3 and the 5. That's index number 2 and number 3. So we really want to go to 2 and 3. And so like you can just think about each of these examples and figure out what's a general expression that describes the first number in all of these. And the second number is always just I.
The next question was whether there were any good resources for learning how to think logically, because solving these problems isn't just about knowing the mechanics of the programming language. You also have to think logically about how to solve the particular problem.
Yeah. Let me, before I don't know about a lot of resources, but let me point out a few things when you're solving these problems. I think there's a tendency, because of the way the educational system tends to work, is to favor and reward memorization, right? Like I've seen this problem, I see the problem again, I know the answer, done. And a lot of mathematics, frankly, is taught that way, and it's pretty bad. And so the thing to take away from these problems is not, you know, this is how you solve this problem, but it's the logic, for example, that John just gave us that said, there's a really nice construct here where you check something. If anything returns false, then you are done. Otherwise, you return true. So what you're going to see in a lot of these problems, it's not about solving stable. It's about the constructs that we use. It's how we put together the constructs and the conditionals and the variable assignments and all of that. So part of the goal here is to really separate yourself a little bit from the actual details of the problem and think about the overall structure of how we're putting these pieces together. And then what you'll see is that those are what generalize across problems. You'll see themes over and over again, right? So there's a finite set of problems we can specify, but what you'll see is that the underlying structure is pretty similar. Well, you'll see patterns across that is what I should say. Maybe John has suggestions for other resources.
Yeah, I thought that was a good explanation. I don't know of any resources about logical thinking that are like really great. Most people learn it kind of by working through a lot of problems in this course. And it's not uncommon at all that it is not something that just comes easily. but practice does seem to help a lot. And there are relationships between problems, just as Hani said. I think that's true, that as you kind of work through more of these problems, you just recognize like, oh, this is pretty similar to something I've seen before. And if it's something you haven't seen before, well, sometimes you can just kind of work it out on the fly, and sometimes you can't. And so that's why practicing a little bit beforehand, just to have seen some similar problems, is a good way to prepare. Okay, so we're going to look at Spring 2020, Midterm 2, Question 2, Part B, and try to focus on the question of, when you make a recursive leap of faith, does it work, I guess, and what can go wrong? So we've already, let's say, solved this power, which takes a positive integer and returns whether s is a power of the base. Okay, and now we're going to do implement powers. A generator function which takes positive integers n and k. It yields all integers m that are both powers of k and whose digits appear in order in n. Oh, fantastic. So what does this mean? You look at the digits that you're given, 1, 2, 3, 4, 5, and you can take subsets of those digits, like just the 2 and the 5. And if that's a power of 5, then that should be part of the result. Doesn't sound easy, but we can take a look. So we are filtering. Basically, like when I see filter, I assume this is about find all of the ways in which you can build up numbers just by taking digits of n. And then we're going to filter them to have only the ones that are a power of k. So this will worry about the power of k, and this will find all the numbers that exist within n. So let's just worry about the numbers that exist within n and talk about kind of building that up recursively. So there's this notion of a seed, and this seed is, I think, the digits that we still get to work with. If there are no digits, then then we can still build one number, which is just 0. Otherwise, we're going to go through something and do something with it. I guess now we have to find some recursive structure. And I think the recursive structure is that if you take a number like this, you could find all the numbers within it by finding all the numbers in 1, 2, 3, 4. And then for each one of those, either stick a 5 on the end or don't. So that will give you all the different possibilities. Is that if you find all the numbers within n divided by 10, all of those are also, oh, sorry, not n, build, or seed. In seed divided by 10, then all those numbers are also in seed. But there's another number within seed, which is what you get when you put the last digit of seed on the end of whatever x is.
By the way, I'm going to come back to Steve's question in a second. We've seen this many, many times, exactly this construct where John is peeling off a number with the integer division and then creating the base. So that's another pattern that we've seen over and over again for this type of manipulation.
Yeah, exactly. And the recursive leap of faith happened right here, where we're kind of trying to list out every possibility. So we assumed we had a way for listing out all the possibilities if I just had a smaller number, 1, 2, 3, 4. And assuming that works, then I can start putting different variants of that. So if I find 12 in there, then I want to yield both 12 and 125.
And noticed here too that John did something very clever at the beginning where he went all the way to the bottom and said, there's a filter. So what must be happening is I'm going to generate all possible solutions and then narrow them down into the ones that satisfy the constraint. So that makes it a little bit easier up top, but now he has to do some hard work.
Yeah, okay, so now let's look at the filter. Now build has given me everything, 12, 13, 14, 134, and in there somewhere is the 1 and the 5 and the 25 and the 125. These are all powers of 5, so I need something that's only true if I call it on a power of 5. Well, that's exactly what the is power, is that what it's called? Yeah, is power function that I implemented in part A does. But is power takes 2 arguments. And by currying it, I get to fill in one argument and then wait until the other argument is available. So the first argument I'll fill in is k. And then what filter is going to do is it's going to call, basically it's going to call is power k on every element of build n, leaving us only with the ones that are powers of k. Yeah, life is so much better if you fixate on an example. So if seed is this, then seed divided by 10 is that. And then the hard part, which is what happens when you build 1, 2, 3, 4? Well, you get 1 and 2 and 3 and 4, but also 12 and 13 and 14, and also 123 and 124, and also 1, 2, 3, 4, and also 0, and also 23. I don't know if I said that already, but that's the thing. That's the leap of faith, is to say build is going to give me all those possibilities, and then all I have to do is like stick a 5 on the end or not. Yeah, good question. So it's about lecture and about using sets and why they're fast, I guess. The built-in set has like 2 useful properties. One, it gets rid of repeats. But the more useful property is about its efficiency, which is that figuring out whether something is an element of a set happens in what's called constant time. So if you watch the efficiency lecture, this means that it doesn't scale with the number of elements that are in the set. So if you have 50 elements in the set, and figuring out whether something's in there takes about as long as if you have 5 million elements in the set. And this is achieved through a technique called hashing, which you get to learn about in 61B. Got to leave something for 61B. So that's like one of the topics that we don't cover in this course, but you could read about it if you want. And it's a wonderful technique. So basically, anytime you're trying to figure out whether something is in a group or in a set, you want to use this particularly efficient technique, which is called hashing, and it's built in to the set. But we haven't really talked about how to re-implement it. You'll do that in 61B. Yeah, so we have an implementation in this project which comes up with the number of elements between here and here. Is that what this does? Well, yeah, they have 5 and 6 and 7. So if instead of writing this code and using sorted lists, we instead had 2 sets, that one and that one, then there's a built-in functionality for taking the intersection between 2 sets. I can get the length of that, and now I have a fast overlap that didn't take a lot of code. Okay, so here's an optional question from lab. Write a function reverse other that mutates a tree. So a tree is input, and we're going to change it such that labels on every other odd depth are reversed. So if we start with 1, 2, 4, 3, then we reverse the order of the 2, 4 branch and the 3 branch. And so, actually we don't reverse the order of the branches. We just reverse the order of the labels themselves. So the branches are still the same structure, except for we've changed the 2 and the 3 to be 3 and 2. Oh, it says notice that the nodes themselves are not reversed, only the labels are. Okay. And here's an example. Okay. Sorry, I got to get all these Zoom things out of the way. So how might we do this? Well, okay, so when you're doing something that's like every other depth, you really have 2 choices. One is track what depth you're on. This is a good way to go. And another is to only process even depths. And then you assume that the level below is an odd depth. So we could do it both ways. I don't know if you all have a preference, but let's try this this notion of process only the even depths. So we assume that T is either the whole tree or it's a branch of a branch, meaning another even depth, that would be depth 2, or it's a branch of a branch of a branch of a branch, that would be like depth 4. That's one way to do it. Okay, so one way to solve this recursively would be just to focus on the first odd layer. That would be the labels of the branches, and then make recursive calls to handle all the other odd layers. So the labels of branches would be b dot label for b in t dot branches. If t is a leaf, then there are no such things. So I guess we can just return at that point. Otherwise, we want to get the reversed labels of branches. So there's various ways to do it. There's a built-in reversed function. I think maybe the well, this is a fine way to do it. We can practice some of the stuff that we've learned in earlier lectures. So reversed is something that I can call on labels of branches. And then I kind of get them in the other order. Now, the tricky part is that I have to take each branch and I have to find the appropriate label for it. So in this example, now I have, which example should we do? Let's do this example. We've got 2 and 6 and 8. Now we have an iterator over 8 and 6 and 2. And that's what we're supposed to slot in as these labels. So we have to go through in parallel the branches so that we can update their labels and the new label values. And we did, in fact, learn about a built-in function that does this called zip. So this would go through every branch and every new label that we get by zipping together t.branches and the reversed labels. And now we will set b.label to be its new label. What about the recursion? Well, we don't actually want to call reverse other on the branch because then we'd have an odd branch as t. So instead, what we want to do is go through all the grandchildren and call reverse other on that. This would be grandchild, sorry. I'll probably do the trick. Let's try it. Oh, doesn't fit. Now it fits. Nope. Probably we need to know what a tree is.
Yeah.
Now it works. You are supposed to know what zip is, but it's kind of an esoteric topic, and you should know what reversed is. But we could actually try to solve this without reversed and without zip just fine. We could instead go over indices, and that would be a fine thing to do. So if we did something like for I in range of the len of b dot t dot branches, we would then find the appropriate branch and change its label to be the label in the like reverse position. One way you could write this is negative I, or if you wanted to be more explicit, you could write len of branches minus I.
Something.
But it doesn't work.
Yeah, something wrong. Oh, is it? Yeah, something seems wrong, but I don't know what it is. Let's see if we can fix it real quick.
Oh, name error. B is not defined. Oh, that's a boring problem. So this needs to be T dot branches.
Oh. See, we were in the wrong line of code. Nope.
No, what's wrong?
It didn't reverse.
Oh,
No, you're going.
this is just the wrong index.
Yeah.
We're gonna fix it.
So
this
do
is
n minus I, or well, you don't have n.
so if this is 0, this needs to be -1.
Yeah, it's. Oh, I see. Yeah,
And
yeah,
when
yeah.
this is 1, this needs to be -2.
Yeah. So it's.
So it's really -I minus 1.
Yeah.
Ta-da!
Classic off by 1 error.
The next question was, what does super do when you have a class that inherits from 2 different classes? Well, good question. So if you use super on a class that inherits from 2 different classes, what have you built? You've built something very strange. But basically what you've built is it's the same object, except for it's going to not look up things in its class. It's going to look at them up in one of the base classes. And which one? Well, it looks at them in the order that you inherit. So if you have a class that inherits from both B and C, it's going to look in B first, and then it's going to look in C to find the corresponding attribute that you're looking up. Fall 18, midterm 2, number 6. Implement replace, which takes 2 non-empty linked lists S and T as well as positive integers I and J with I less than J. It mutates S by removing elements with indices from I to J and replacing them all with some other list T. Afterwards, S contains all the objects in T, so a change to T would reflected in S as well. T may change as a result of calling replace. Okay, so it's okay to change T. And we assume S has at least J elements. So what's going on here? If we had printed this out, it would say 3, 4, 5, 6, 7. And then we replace elements from 2 to 4. So that's the 5, 6 elements. That's element 2 and element 3, but not including element 4. So now we have 3, 4, something, something, 7. And what's that something, something? Well, it's the elements in T, the 0, 1, 2. So we're left with 3, 4, 0, 1, 2, 7 instead of 3, 4, 5, 6, 7. And this is supposed to demonstrate that if you changed T, T.rest.first equals 8, that's changing the 0, 1, 2 to a 0, 8, 2. This is also changing S. So now we have 3, 4, 0, 8, 2, 7. Whew. Well, I think this is not going to be that quick, but let's take a look. If I is greater than 1, then we're kind of not where we need to be to make the change, I think is the story there. Because with the linked list, you can kind of only change the first thing and the rest, but things later on, you'd usually handle with recursion. So, oh, I can use PDF annotation. That would work much better. Uh-oh. Can you not see my screen anymore?
We see your screen, but no annotation yet, John.
Okay.
Now we have it.
So if I is greater than 1, then I think we need to just kind of move on. It's the same thing as replacing the rest of S with T with a smaller I and a smaller J. So how did I get that? Well, basically like replacing 2 to 4 with an S is the same thing as replacing 1 to 3 within S.rest. That was the idea there. Okay, so we've kind of moved forward into S until we find the place where we're going to make this edit. We've found this place where I equals 1. Is I ever 0? No. Positive integers I. Okay, so now we basically know that I is 1. And that means we're going to make some edits. This says k times, or sorry, j minus I times, so kind of the length of the part that we're removing, which would be like 4 minus 2. Okay, so we need to remove 2 elements. We need to remove the next element. And we saw this in lab as well. You can remove the next element by changing s.rest to be s.rest.rest. So what did this do? This just remove element at index 1. Okay, so just like in lab, that's how you get rid of the element at index 1. We're doing it a bunch of times, j minus I times, in order to kind of get rid of all the elements that we want to get rid of. Okay, now we have an interesting expression, end equals t. While something end equals n dot rest, I think what we're doing is we're finding the last element in t.
Yeah.
How would we find the last element in t? Well, we'd start at the beginning, and then if we haven't reached the last element, then we move forward in t by calling end equals n dot rest. How do we know that we've reached the last element? If end dot rest does not equal link dot empty. So it might be that t only has one element and we've already reached the end, in which case we need to make no updates. But if not, then we need to continually go through end until it really is the end, until there's nothing after it, meaning the rest of it is empty. Now we found the last thing in t.
By the way, when you see that end equals n dot rest, that's basically I equals I plus 1. You're incrementing through a list. That's a classic, how do you make your way through a list?
Yeah, exactly. Great point. And so now I think we found the end of t. We know where we are supposed to be splicing in this t, which is right at the position 1 within S, because I is 1, remember. So we're going to change s.rest to just be t. But what about everything after? Like, what about the old s.rest? That's supposed to appear after t, which means we can change the end of t to be everything that used to be in s.rest. Oh, I don't want to sign this. I want to.
I don't know. It's you can consider it artwork, John. I think you should sign it when you're done.
There we go. So, let's think about this example. What we did is we had 3, 4, 5, 6, 7. We kind of worked our way past the 3 until we just had 4, 5, 6, 7, and I was 1. Then we got rid of the 5, so we had 4, 6, 7. We got rid of the 6, we had 4, 7, and that was called S in our recursive call. S was the link 4, 7. Now we found end. End started out being 0, 1, 2, then we went to the rest, so it was just 1, 2, and then we went to the rest, and we found that the end was this link 2. And then we made the following updates. After 4 comes t, which was 0, 1, 2, and after 2 comes whatever used to be after 4, which was 7. And then we ended up with 3, 4, 0, 1, 2, 7.
Think about it. Imagine you have a train that's connected, all the cars. We essentially deleted a bunch of cars, and now you have 2 pieces, and you have to splice something in. So that requires 2 splices at the front and at the end. Yeah. So that's basically what's happening here. That's why you have to keep track of those 2 places.